Good afternoon, everyone, and welcome to ASL's presentation today on the resilience to variable renewable energy lulls. I was hoping outside it'd be overcast and dreary and still, but it's blue skies and breeze blowing here. So, alas, we will push on. Today, my name's Tim, and I'll be facilitating today's session as well as the Q&A session at the end of the presentation. I'd like to start the session today with an acknowledgement of country. I acknowledge the traditional custodians of the land, seas and waters across Australia and honour the wisdom of Aboriginal and Torres Strait Island elders past and present and embrace future generations. Today I'm presenting from the lands of the Juggerah and Turrbal peoples, and more specifically I'm in Mount Gravatt, whose name, Kagur Madul, means place of echidnas, which was once a significant habitat for these animals in this area. The echidna is also a significant symbol for the Jagera people, representing respect towards elders, ancestors, and teachers. I'd like to start, just go through a bit of housekeeping for today's session. Many of you will be familiar with this, having attended webinars before, no doubt, but microphones will be muted and cameras should be turned off. Today we'll be using Slido for the Q&A session. There's a QR code and some details on this slide, and the QR code also appears throughout the presentation. So I encourage anyone who has questions to use the code and submit those during the presentation, and we'll seek to answer them during the Q&A session. This webinar is being recorded and will be published on our ASL website alongside with the slide pack we are presenting today. There are already additional materials in relation to VRE Lulls up on our website through the 2025 Infrastructure Investment Objectives webpage. That report provided through Appendix 3 an in-depth detailed look at VRE Lulls, and the methodology we're using will be discussed today. If we move to the next slide, we have 4 people I'd like to introduce to today. We have Melanie and Shira, the General Manager and Senior Manager in the System Planning Financial Markets team here in ASL. We also have Dominic Price, who will be our main presenter today, who also sits within the same team. And we have Stuart Browning joining us, who is a climate scientist from Risk Frontiers, who provided assistance to ASL during the development of the 2025 IEO report. I'll hand over to Melanie now, and then we'll kick off with today's session. And thanks again for joining.
Thank you, Tim, and welcome everyone. If we just go back one slide, sorry. Today, the team that you see on the screen will be speaking to you about some work that we undertook as part of our 2025 Infrastructure Investment Objectives report in our role as the New South Wales Consumer Trustee, where we do system planning, perform a system planning function. And when we prepare an IAO report, we actually have a regulatory requirement that we must take into account the resilience of the New South Wales electricity system in relation to lulls in variable renewable energy, including by reference to climate modelling. And so that term climate modelling is included in a regulation set by the New South Wales Government. So it's clearly been identified by the New South Wales Government that it's critical to understand risk to the New South Wales electricity system from climate variability, both current and with climate change. So to answer this question, we started to explore what the climate modelling community had done to understand lulls in variable renewable energy, and also what the energy market modelling community had done. And we identified a need to bring together these two communities to better inform our own system planning. And so that is what the team is going to present to you on today. But there's still a lot more work that we can do and further analysis that we've identified. So I'd firstly like to thank you for participating in today's webinar and invite you to contribute to further evolving this work, and the team will expand on how you can do that throughout the presentation. But I'll now hand over to Dom to kick off. Thanks, Dom.
Thanks, Melanie. We'll dive straight in. What is a VRE lull? The general definition we have here is that it's a period of sustained low output from wind and solar generators. This is just a general definition, but later on we'll walk through more specifically how we've defined it for our analysis. These events are also called dark doldrums and Dunkelflaut. VRE lulls are becoming increasingly important as our electricity system becomes more dependent on the weather, and as that weather system is changing with climate change. So yeah, it's very important we understand the possible realms of future weather and the operability of the electricity system during future VRE lull events. We at ASL are the New South Wales Consumer Trustee, which means we have a system planning role for New South Wales. And as it was mentioned in August just past, we published our 2025 Infrastructure Investment Objectives Report with a 20-year development pathway and a 10-year tender plan for New South Wales generation, long duration storage and firming infrastructure. And as Melanie mentioned, we do this analysis as per the regulations, and what we published in August is what we will deep dive into today. Next slide. We will take you through a literature review, walk through our modelling approach, and then step through the two parts of our analysis. The first part is focused on the impact of climate change on VRE lulls, and the second part looks at the resilience of our development pathway to those VRE lulls. We'll talk to a community of practice, which we are initiating, and we should have 10 to 15 minutes at the end for Q&A. Next slide. And one more. So by no means are we the only group in this space. There's a lot of great literature out there that we have learnt from and built upon. For starters, AEMO's ISP modelling approach is the foundation of energy market modelling in Australia. And for the capacity expansion planning in that model, they rely on a 14-year historical data set, which dates back to 2011, and they assume that weather rolls forward in time. And there's been an asserted effort from lots of groups on this slide and others to sort of increase the size of that weather data set, looking back further to the 80s when modern satellites came about, or even further back, in an attempt to better understand what is the 1 in 20-year VRE lull event that we need to be prepared for, or the 1 in 50-year VRE lull event. As part of our IAO, we've used climate projections, which are calibrated to historical data, which has been a significant uplift in approach. This means we're able to create a really large data set of weather years. It's sort of 280 weather years per forecast year, and we're able to capture the potential impacts of climate change. I'll pass to you, Stuart. You can talk us through some of the climate literature.
Yeah, thank you, Dom. As Dom mentioned, we did, before commencing this work, we did a thorough literature review because we really wanted to make sure we spent most of our efforts on building on existing knowledge and not really reinventing the wheel. And I guess one of the first places we started was a great piece of work that got done a few years ago, which was the Energy Sector Information Project. And this was really useful. A group of scientists got together from the Bureau, CSIRO, and the other groups in Australia that produce regional climate model simulations. And they did an evaluation of all of those simulations and recommended a set of models that should be used to provide a balanced view of future climate. And they also bias corrected those model simulations and put them in a consistent format that was really much easier for the electricity sector to use to better understand future climate. They used these data sets to produce some case studies looking at relevant hazards. And I've used these data sets since they first came out. And I think one of the great things about this was to have an authoritative source that had evaluated the data sets that we could reference and use. In terms of looking at VRE Lulls, which is what our project was about, there was some really good work came out a couple of years ago from Potter et al. And what they did was they used regional climate model simulations to look at possible future changes in solar radiation. So looking at the potential for solar lulls. And what they found across Australia was that there was going to be an increasing trend in clear sky days. So solar availability would increase in the future. And we'll get to this later, but that's similar to what we found looking at newer data sets. Also, there was work by Capicia, which was a similar project to what we were attempting to do, but it was focused in Europe. And what they did was they looked at solar and wind lulls throughout Europe. And although they found different changes in different regions, I think one of the most interesting aspects of this for us was that because they looked at all of Europe, there was this geographical diversity that meant when there was lulls in one country, there weren't in other, and it kind of balanced out. And so their network, once connected, was quite resilient to lulls, rather than if each country, small country, acted independently. The Richardson et al. Study was really, really useful for us. It was quite recent and relevant. And what they did was they did basically a comprehensive climatology of VRE lulls across Australia using historical data. And this was a really great piece of work. And we chose to align our methodology closely with this recent work, but taking it into the future by also using newly published future climate model projections. And I guess the last one that really deserves a mention here was the Kittle et al. Work, because they provided us with some guidance on a suitable way to define lulls. So we could define lulls either in terms of resource availability, so was there a lack of wind or solar, so looking purely at the weather and climate data, or a second approach which considered positive residual load, so looking at times when electricity demand and supply were out of balance and supply was falling short, which is a more comprehensive way to look at it and important to quantify potential impacts and looking at firming and storage requirements. So we've taken a little bit from both of those approaches in our defining and examining of lulls. Next slide, please. So we're really lucky when we commenced this work because it coincided with the release of a whole new generation of climate data sets for Australia, particularly the Barra C2 reanalysis. So this is a high resolution reanalysis that provides us with 4-kilometre resolution at hourly time steps historical data for all of Australia back to 1979. So it's the most complete data set. It's produced by the Bureau of Meteorology, and it's a very, very good tool for us to understand how lulls have occurred in the past and something that we can calibrate our future climate model data sets against. We had a look at a few different sets of the newly released regional climate model simulations that have come out over the past couple of years, and we ended up using the Bureau of Meteorology's BARPA regional climate model simulations. And these consist of 7 global climate models across 2 warming scenarios, an optimistic future where global warming is capped at a reasonable level, and a worst case scenario, which we hope doesn't happen, which will be very difficult to adjust to. And these global climate model simulations were dynamically downscaled with a regional climate model, which is kind of like feeding a coarse resolution global climate model into the weather model that we typically use for predicting weather over the timescales of days to weeks. And that gives us high resolution simulations across all of Australia that we can better use to understand changes in wind and solar, which we're looking at in this study. Next slide.
Jump in here. So this is our specific definition of a lull for this analysis. It's a multi-day event where both wind and solar output across the entire NEM is sustained below the 5th percentile based on recently observed history. Now, there is no single standard definition for a lull. Different groups would define it slightly differently, and that might result in slightly shorter or longer events. But our definition results in lulls which range in duration from 4 days long, which would be a common 1 and 2 year event, up to 12 days long, which would be a rare 1 and 50 year event. We apply this definition slightly differently across the two parts of the analysis. In the first part, we're trying to isolate the impact of climate change on lulls. And so we apply that definition to wind speeds and solar radiance data across the NEM. For part two, we're trying to sort of assess the resilience of our electricity system. So we overlay the capacity mix, sort of where wind and solar projects are located, which impacts the duration of the lulls. This chart on the right is a duration curve of the daily average capacity factor of VRE across the entire NEM from the 2024-25 financial year. And the 5th percentile there is equivalent to a capacity factor of about 20%. So our VRE lull events have a NEM-wide capacity factor below 20% each consecutive day. That's how they're defined. And so it's worth noting that there aren't days projected that have 0 VRE across a day. There is always some energy generation from renewable energy, and that 5th percentile of 20% is I think higher than most may expect. Next slide. And just briefly how we've defined resilience. It's the ability of the system to limit the severity and duration of system degradation following a lull event. So that, for this analysis, includes the ability of our development pathway to meet the reliability standard. But the analysis we've done is broader than this and less deterministic than that. We've also looked at the implications of relying heavily on other sources of generation like hydro and gas. And we've also explored the impact of these lull events on wholesale prices in New South Wales. Next slide. And Stuart will take us through part 1 of the analysis.
Thanks, Dom. So what we have on this slide are maps of the frequency of solar lulls. So we've defined our lulls, as Dom mentioned, as days when solar irradiation is below the 5th percentile. So we're not looking at demand or anything here. We're just looking at the availability of solar energy. And the 5th percentile there is around about 110 watts per metre squared for those interested. Now, the days when there is a lull are usually cloudy days, and they usually occur in the winter months when the days are short and the sun's at a low angle. So there's a very strong seasonal component to solar lulls. And these maps of the NEM show present day solar lull frequency on the left. So for Southern Australia, this is about 50 to 100 days and per year. And for Northern Australia, Queensland and the Northern Territory, it's close to 0. So they don't really get many solar lulls in the northern part of the country. Now, for future projections, and they're the figures, the two figures on the left there, We've taken a 20-year average around each of those dates. So 2050 is represented by 2041 to 2060. And then we average across the 7 models. And these are for the SSP 370 scenario, which is really our worst plausible case. So this gives us a good idea of how these lulls might change in a warmer climate. And by doing all this averaging across years and models, we're really focusing on the climate change signal and kind of filtering out that year-to-year variability that you might see on shorter timescales. And what we see in these figures is that solar lull frequency is either staying much the same or decreasing everywhere across Eastern Australia. There's nowhere that's going to see an increase in the frequency of solar lulls. And the largest decreases, so this is an increase in sunny days, will be over southern Australia. And the main reason that this is expected to occur is that as the climate system warms, we expect the subtropical ridge, so that big area of high pressure that typically sits over Australia, is expected to strengthen and expand. And what this means is that we'll have more frequent and stronger high pressure systems, more sunny days, and it will displace fronts and cloudy conditions further south away from the continent, leading to more sunny days. Next slide, please. So these are similar maps looking at the frequency of wind lulls. So again, we've defined a wind lull as when the NEM-wide wind speed is below the 5th percentile, which is around about 18 kilometres an hour. So these are days with wind speeds below about 18 kilometres an hour. And what we see here, there's fair diversity over Australia, but where we have more complex terrain, particularly along the east coast, we tend to see more frequent lulls in wind speed. Now, looking to the future, as that subtropical ridge strengthens and our fronts, which are our windy weather systems, are displaced further south, we expect to see an increase in the frequency of wind lulls across southern and eastern Australia, which is what these figures here show at 2050 and 2090. The red shows that the frequency of those lulls will be increasing, whereas over parts of northern Australia, particularly coastal Queensland, we're expecting to see a decrease in the frequency of lulls into the future. So if we look at the entire NEM, those increases in lulls in the south and southeast are probably going to be offset by those decreases in the north. Next slide, please. So this is where we look at the actual frequency of or projected changes in the frequency of lulls, and these are calculated across all of the renewable energy zones in the NEM. And on the left side are the frequency of solar lulls in red and the frequency of wind lulls in green. And on the figure on the right are the combined wind and solar lulls, so our compound lulls. Now, the values shown here with the dots on those charts are the 20-year averages taken across 7 models and both scenarios. And the shading is indicative of interannual variability, so year-to-year changes, what you might expect from one year to the next. So we've got our long-term average there in the solid colours, and the shading, it could be, up to 20 or 30 days per year, or as low as 10, for example. Now, the key takeaway here is that solar lulls are expected to decrease in frequency, which we saw from the maps previously, while wind and compound lulls are expected to stay pretty much the same. And the main reason for not much change in these is mostly down to the diversity across the NEM, which we saw before. While wind lulls will probably increase over southern Australia, this will probably be offset by a decrease in lulls over Queensland. Next slide, please. We also had a look at the weather patterns associated with historical lulls. So the maps on the right show from the top temperature, the middle is cloud cover, and the bottom map is mean sea level pressure. And so these characterise the typical weather patterns that we wanted to look at that were associated with lulls. And this is really revisiting some of the work that was already done by Richardson et al., looking at historical lulls and the climatology of those, and we got very similar findings. I guess one of the more interesting things is that solar and wind lulls typically occur under different weather patterns. In general, when it's not windy, it's often sunny, and when it's not sunny, it's often windy. But there are times when we both have a lack of wind and cloud cover, and that's when we get our really severe compound lulls. I guess one of the interesting takeaways from this is that during solar lulls, when it's cloudy during the daytime temperatures are lower. And since solar lulls mostly occur during winter, this can increase electricity demand. Don, would you like to expand on that a little bit?
Yeah, it's an important correlation. The winter lulls do correlate with lower maximum daily temperatures in New South Wales, and every 1 degree reduction in temperature corresponds to about 3 to 7 degrees increase in demand, because more consumers have their heating on. And so it is a double whammy in that we have, low VRE and high demand.
Great, thank you. And the next slide, please. So we also looked at projected changes in rainfall, because the rainfall, of course, is important for our stream flows, our dam supplies, and of course the generation of hydroelectricity. So these maps are similar to the ones that I showed previously. Present day annual rainfall is on the left, and projected changes at 2050 and 2070 are on the right. And you may be able to see some circles there of varying sizes on the map, and these represent the locations of hydropower stations. And what these figures do is they really just support a fairly long-held scientific consensus that rainfall across Southeast Australia will most likely decrease under a warming climate. And this also is related to that strengthening of the subtropical ridge that I mentioned before, because as we get more frequent and stronger high pressure systems over southern Australia, and our rain-bearing weather systems are pushed further to the south, we just end up with less rainfall overall. And this is the main thing that's driving this decrease in rainfall across Southeast Australia. Of course, the implications here are that most of our hydropower generation, including the Snowy Mountains, are located in this region with projected declining rainfall. So this is something to also be considered when thinking about the availability of firming, for example, from our hydroelectric power generation. Thank you. And next slide, please.
Thanks, Stuart. I'll talk us through part 2 of our analysis, which focuses on the resilience of the development pathway and our electricity system to VRE lulls. For this part, we selected 15 VRE lull cases that we observed from the projections. And those cases, the duration of those cases are shown in the chart here. We selected a range of different severities that have a different probability associated with them. And we looked at 3 different forecast years, sort of today's system, in 5 years, and in 10 years' time. And a key point here is that the duration of the VRE lulls is projected to decrease over this 5 and 10 year period as the diversity of VRE in our system increases. So if you focus on the 1 and 50 year lulls in black in this chart, you can see that they decrease in duration from 12 days to 10 to 9 days long. And over that period of time, our development pathway expands wind and solar projects in new renewable energy zones, areas which have a different generation profile to other areas in the state or in the NEM, and any additional anti-correlation does support resilience. It's far less likely that we have consecutive days of low availability from renewables below that threshold if we spread out our capacity to new renewable energy zones. And so, yeah, the key point here is that the diversity of VRE is itself a form of resilience to lulls. You can jump to the next slide. This is a case study based on one of those 15 cases from the previous slide. It's looking at a 7-day VRE lull. It's a 1 in 20 year event projected for 2035. It falls in June in winter, which means demand is higher than typical. The charts here show New South Wales dispatch of generation across the 7-day period. And on the left, we have a typical weather conditions case just for comparison. And on the right, we have the VRE lull case. The first thing to observe is how VRE is far less. In typical weather conditions, there are days where solar in yellow and wind in green provides all of our energy in the middle of the day. So on the left, you can see below the x-axis, we have hydro in blue pumping and battery in purple charging up. When we move to the right, there's far less VRE, but it's also not nothing. There's still a material amount of wind and solar contributing to demand. It's equivalent to a capacity factor of 13% averaged across the whole 7-day period, which is probably only less than half of average. But you can see in the outcomes that we're replacing the lost VRE with hydropower in light blue, gas in aqua, battery in purple, and imported energy in light purple. There was no unserved energy in this simulation, so the system was resilient, relying on those other sources of generation. You'll also notice there's still charging of batteries throughout the period, so storage still plays a role in shifting energy from periods where there's not as much stress to periods of higher stress during the lull. And because these are NEM-wide lulls, in the start of the lull, we are imported energy into New South Wales, but we actually have to export some energy to Victoria in the second half of these periods because they're NEM-wide events. So that limits the ability of the system to solely rely on imported energy. We can jump to the next slide. This slide just draws out the amount of generation being provided by hydro and gas in New South Wales. That's what the two charts at the bottom here, where the coloured line shows the lull period, the 7-day period, the same case. And in grey, we have the generation from that technology type during typical weather conditions. And so we are reliant on a very high sustained output of hydro and gas generation during these periods. What's interesting for hydro generation is over this 1 week, we only reduced New South Wales reservoir levels by about 10%. So the limiting factor wouldn't be the reservoir in this instance, it would be the capacity output of hydro generation. And for gas generation, this level of output is higher than what's been observed historically, and is beyond what the sort of pipeline gas system can provide. So this does rely on either an upgrade to that system or secondary fuels on site at the power stations. We can jump to the next slide. This slide just illustrates all 15 cases that we simulated and summarizes the dispatch outcomes just in one column each, which shows the average power per technology type. Maybe the first insight to draw on is for the 2025-26 cases, you can see a large portion of generation is provided by coal power. But as we move forward to 2030 and 2035, our modelling does assume that New South Wales coal power retires. I think in the 2035 year, we just have the one remaining coal power station. And so meeting demand during these periods is still VRE, a substantial amount. You can see it meets about half of demand in many of those cases there in 2035. And as I mentioned earlier, hydropower, gas power, battery, and imported energy are also supporting. Across all these 15 cases, there was only one case where we observed some unserved energy and it did not breach the reliability standard. We can jump to the next slide. These are the wholesale price outcomes across the 15 cases. The chart here shows the increase to New South Wales wholesale prices during the VRE lull events on average, compared to typical weather events. So it's an increase in wholesale price. And it is material. It's quite high, particularly in 2030 and 2035. During these events, we are reliant upon the most expensive forms of electricity to maintain resilience, and that has an impact on prices. We may have expected that there would be a relationship between the longer VRE lulls and a higher impact on wholesale prices. But what we found in the modelling is it was sometimes some of the shorter lulls had a bigger impact on the wholesale price. And that's because of sort of a few characteristics that aren't necessarily captured in the way we've defined VRE lulls that do have an impact on the system. So one of these is the depth of the VRE lull. Some of the 4, 5, or 6 day lulls just had 1 or 2 particular days where VRE was very low, and that had a big impact on prices. The demand that occurs during the lull had a big impact on prices. Some of the lulls were observed to occur in April, where demand for electricity is quite moderate, and so that didn't have as big as impact, whereas the ones in June and July did. And thirdly, the conditions in New South Wales has a big impact on New South Wales price outcomes. But the way we've defined lulls is that they are NEM-wide. So the extent to how different regions had VRE impacted these outcomes. But still, generally speaking, the longer VRE lull events had a bigger impact on wholesale prices. We can jump to the next slide. So we have deemed that the development pathway does maintain resilience to various severities of VRE lulls. We've shared that it does have a big impact on wholesale prices, but the amount of unserved energy observed was minimal. But we also acknowledge that there are limitations to this modelling, and that does leave risks. The 3 sort of main drivers of this resilience, the first we've talked to many a times, the diversity of VRE. We're not projecting any week-long periods where we have no VRE, or even day-long periods for that matter. It does still support meeting demand, particularly if it's diverse. The second point we haven't discussed much, and that's the increase of network capacity. And in order to unlock diverse VRE, we do need transmission. Our model does assume over the first decade that we expand VNI West and Hunter Transmission Project and QNI Connect and some key transmission projects for New South Wales, which allows that diverse VRE resource to be accessed and sent to the Sydney, Newcastle, Wollongong load centre. And thirdly, there will certainly still be a need for increased storage and firming infrastructure. There might be instantaneous periods where there's very low VRE, and so there is a requirement for dispatchable capacity. Finally, some of those limitations I spoke to, or just the various assumptions we have had to make about how VRE Lulls are represented and how the NEM has been dispatched. Generally speaking, there is uncertainty in climate projections, and in our dispatch modeling, the use of perfect foresight can overestimate how well technologies like storage can operate. And then more specific to our methodology, the demand we assumed during the lulls we saw has a big impact on the outcomes. And there is uncertainty in future demand and what we've assumed. The continuous high sustained output of gas and hydro during those VRE lulls is uncertain, which we discussed. And we also use a simplified sort of representation of the NEM. We don't model the sort of detailed network constraints in our time sequential modeling for this exercise. We jump to the next slide. Yep, and one more. So we are eager to continually improve this modeling. And so we are initiating a community of practice, be titled Climate Science for Electricity System Planning. And so we're inviting any individual who's passionate and interested to come join, whether you're from academia, government, a market body, or industry. We want to facilitate more collaboration, particularly, as Melanie mentioned, between the energy market modeling communities and the climate science communities, given how this topic really relies on both of those spaces coming together. And we want to spark more innovation and more learning. So please register if you are interested. We can go to the next slide. And I think we are ready for any questions.
Thanks very much, Dom. And thanks to our presenter also, Stuart. We do have quite a few questions that have come through the Slido. If people are interested in a particular question, feel free to uptick those. I'll try to group them as I can as we work our way down the list, and we'll try to get through as many of these questions as possible in the remaining 15 minutes of the session. But might kick off with the most popular question. How can ASL be sure the implications, or just moved on, let me just highlight that, sorry. The implications on VRE lulls if there is less wind deployment than expected and more solar BESS.
Yeah, so in our market model does assume a fairly high portion of wind is deployed. We do have some build limits in the near term, which restrict the amount of wind expansion to levels we're sort of observing in the market. But beyond that, our market model is an optimal pathway and a market signal. So we do have a high portion of wind. And wind energy is particularly good at adding diversity. There's a higher anti-correlation between wind resources in different reses across Australia than there is solar. Where wind might have more sort of micro pockets behaving differently, solar is a little broader and how it impacts the east coast of Australia, I can pass to Stuart as well to comment on any of that. But I would expect that would make the VRE lulls longer if we had less wind in the system. I don't know if you have anything to add to that, Stuart.
Yeah, I think that's mostly correct. I mean, overall, we expect a decrease in lulls from solar, which would be a positive because we can have more sunny days. But yeah, individual events could end up being much worse if there's less diversity in the resource capture from different resources in solar.
Thanks for that. The next question I have here, most of these questions are for you, Dom, so prepare yourself. How can ASL be sure its plans are resilient to lulls when they rely on unrealistic gas hydro operation?
So our assumptions around the operability of gas and hydro align with the 2024 ISP. So we do rely on that assumption set, and we have to make some assumption about how they're going to operate. And I suppose because we have to act in the long-term financial interests of New South Wales consumers, we also don't want to be overly conservative and have a plan that's overbuilding the system. So we have to draw the line somewhere. If we find in time that those assumptions are, unrealistic, then, we'll update our plan. We redo this modeling every 2 years, and we're able to update our development pathway and tender plan to respond to things like the operability of gas and hydro, and also the delivery of wind compared to solar. We would update our modeling and planning. And I suppose it's we've had to sort of define what lulls are and even define what resilience is for ourselves. So we do think that based on that modeling, the system's resilient.
I think also
Maybe I'll just
sorry. Oh, sorry, I'll go. Sure. That some of the larger reliance on gas and hydro happens towards the 2035 year, so that gives us some comfort that we've got some time to better understand the maybe different scenarios around gas and how hydro might operate. And this is certainly something that we're looking to explore in our next set of this analysis, which will be for the 2027 IAO report.
And maybe just to add finally, because it is it's a very important question that we're quite transparent about in the report as a kind of a key limitation of the analysis. We're also kind of developing this community of practice to have input from this community into how to think about the way that we consider resilience and VRE lulls in the future. So definitely an open area of exploration for the future as well.
Thanks for that. I did see a question pop up which I can actually answer, and that was if slides are going to be available after this presentation. So I can reiterate that both the presentation and the slides will be made available on the ASL website. But moving to the next question, how did you land on the 1 in 2 year and 1 in 50 year event frequency thresholds? Why did you not also consider longer lulls, such as 1 in 100 years?
I can let Stuart add to this, but from what I understand, to be confident in representing what the 1 in 50 year event is, you'd want to draw from a data set that has well more than 50 years. And so I think we had 280 weather years for each forecast projected year. And at a point that, that isn't a good indication of what the 1 in 200 year event is. You just want a way larger data set to be confident in asserting kind of that probability and duration. So I think we were happy to settle on that as the highest risk event, 1 in 50 years, that we could be confident about, and we wanted the whole range of severities down to 1 and 2 year events.
Yeah, thanks, Tom. I can add to that. That's pretty much correct. We started by sampling from the regional climate model simulations. We had 7 models over 2 scenarios and taking 20 years to represent each individual future year. It gave us a sample of 280 years from which we could build our distributions. We calculated the ARIs by fitting an extreme value distribution to those. And while I can certainly give you 1 in 200 or 1 in 500 number out of that, the uncertainties do increase quite significantly when you go to those longer return periods. Potentially in the future, we could revisit this work using larger data sets. I did notice a question in there about why we didn't use NARCLIN. We did actually start the project with NARCLIN, but there were some technical difficulties, which they will hopefully resolve soon. So perhaps in a future iteration, we could build a much larger sample of data by incorporating the NARCLIN modelling as well, and that will allow us to get at those longer return periods.
Thanks for that, Stuart. I might move on to the next question. There's a few questions around network constraints and interregional flows, but let's just start with this first question here, Dom. Can you confirm if network constraints were modelled, and if you can touch on some of those interregional flows, that might be useful for other participants?
Yeah, the time sequential model settings we use has sub-regional sort of representation of the NEM and constraints, which is not detailed network constraints. That's a simplification we make for our time sequential model, which is a limitation. I don't know if you wanted to add any more to that, Shira.
Yeah, I guess in terms of imports and exports, that element of the question, Dom touched on this earlier in the presentation, but the way that we had defined lulls is not New South Wales specific. It does look at the whole NEM, and that means that sometimes even when we've got a lull, and I think one of the actual examples in this presentation around during a lull, at some instances, New South Wales actually exports electricity to other states, despite it being a lull, because other states also have a lull. And so the kind of flows across different regions were certainly considered. And in the context of each lull, we saw different patterns around import and export between those regions, depending on the specifics of the lull conditions.
Thanks, Shira. There's a few questions on reliability and USC as well. How did you assess the reliability standard was not breached if you only modelled individual events?
Yeah, good question. We only had one case where there was unserved energy, and if we modelled the whole year in its entirety, and in that year itself, it did not breach the 0.0006 interim reliability measure. But it's a good point that if there could have been a USC above the reliability standard in one particular year, and that's not necessarily a breach if you consider the low probability of that event occurring. So it was simple for us because there was such minimal USC that it was sort of obvious that there was no breach. But if there was USC, we would consider how much USC and sort of multiply that by the low probability of that occurring to determine if there was a breach or not.
That's sort of an interesting question for policymakers. The previous question around why didn't we model a 1 in 100? Well, if we had modelled a 1 in 100 and that had a breach in USC, that might not necessarily have breached the reliability standard. So I think it's sort of a question for policymakers. Are we expecting to have the system resilient to 1 in 100 year events, or is the reliability standard fit for purpose?
Great, thanks for that. I'll move on to the next question. Have you considered the time for gas, BESS, and hydro reserves to refill after a lull? If no, how often can lulls happen with only a short span between them?
So we haven't focused particularly on sort of two lulls that occur back to back. You know, we do model an entirety year of weather data, and you know the perfect foresight in the time sequential model can allow sort of the storages to be filled up or charged up prior to the lull, which is a limitation. So I think the level of storage at the start of the lull is very important for how resilient the system is. It depletes by the end, and no, we haven't looked at back-to-back lulls, but no doubt as the system depletes its storages, that the second lull would become challenging. I mean, the time sequential model certainly requires storages to be charged or pumped, but it operates with a degree of perfect foresight, which is a limitation.
And we did see that BESS was recharging in the case study that Dom presented. We saw that BESS was recharging during the lull period and sometimes recharging while gas was operating, which was quite interesting, recharging from gas.
Thanks. I might quickly jump to this next question on hydro generation while we're talking, and then we'll probably might move to the demand side after this. But hydro generation appears to be capacity constrained. Is there potential for high hydro generation capacity for VRE Lulls?
I'm not sure I fully understand the question. There are constraints applied to hydro generation, and I think our general feeling is that it's operated at higher sort of sustained levels than we've seen in the past. Is there potential for it to operate even higher or less constrained? I don't know.
Yeah, I guess one, not sure if this directly answers the question either, but in terms of the assumed infrastructure, hydro infrastructure in the system, we sort of just assume that the existing infrastructure that we currently have for hydro generation continues to exist in the future. We don't necessarily increase the capacity, the megawatt capacity of existing hydros, but we do have in the infrastructure investment objectives report, within which this analysis sits, additional pumped hydro that's assumed to enter in the system as part of the development pathway. So we do actually end up increasing the capacity of hydro in New South Wales through the forecast, but that's additional hydro as opposed to, and pumped as well, as opposed to the current existing hydro plants.
Thanks, Shira. There's still lots of questions, but probably got time for one more. So I might ask this question around demand side response. Was it considered in the analysis, Dom? And there's also a question that's been asked around also consideration of consumer energy resources.
Yes, both are considered during the lulls. The assumptions we've used on both align completely with the 2024 ISP. There's definitely demand side participation, which kicks in when the price sort of reaches a high enough level. I think it's relatively small. It's assumed trajectory compared to other sources of generation. On the consumer energy resources side of things, yes, it's still assumed, and I think a large portion of it is assumed to be orchestrated as well. So it's not responding to the lull in the time sequential model as such, but it is assumed to align with kind of high and low demand periods in the model. And then there's another portion of C, consumer energy resources, which is less coordinated and not kind of aligning as nicely with the tight supply demand periods.
Great. Thanks, Dom. We are at time, so I recognise people's time is valuable. So a big thanks to our presenters today, but also to the audience for attending. There's lots of interest in this topic, and it's great to see so many people engaged, and thanks for the questions. and hopefully some of those that we didn't get to can be explored further in the community of practice. But I will let everyone go and wish you a great afternoon and talk to you later. Thanks very much. Bye.